A matrix can be thought of as a collection of numbers arranged in a certain pattern. Now, a matrix may emerge mathematically from a lot of different sources. One source for a matrix is a system of equations. Here we have a system of 3 equations and 3 unknowns. And actually we can think of 2 matrices emerging from this system of equations. One matrix is called the coefficient matrix because it is composed of only the coefficients of the variables. Here I have 1, -2, 2. And in the coefficient matrix at the top I have 1, -2, 2. And the next row is -1, 3, and then no z's means 0 for that entry in the matrix. So -1, 3, 0 here. And then 2, -5, 1, 2, -5, 1. So coefficient matrix. Now when we add to the coefficient matrix the constants over here and just tack on another column for those constants, then we have what's called an augmented matrix. We can think that the coefficient matrix is augmented or enhanced by the appearance of our constants. Now, a lot of times when an augmented matrix is written, the position of the equal signs here is indicated with a dotted line of some kind. But it's really an optional kind of thing. I'm not going to use the dotted line because it takes up a little time to write it. And if we understand how we have laid out our matrix and we understand the position of those equal signs, then really this is not a necessity. Now, in terms of just our conversation with matrices, a lot of times a matrix is designated by the number of rows and the number of columns. Now the rows go this way and the columns go this way. So this augmented matrix has 1, 2, 3 rows, and it has columns 1, 2, 3, 4. So this is called a 3 by 4 matrix. And that's called the order of the matrix. So the order of this matrix is 3 by 4 because it has 3 rows and 4 columns. Now this matrix has 3 rows and 3 columns, so it's a 3 by 3 matrix. That's its order. And when the order of a matrix is the same number, that is, it's 3 by 3 or 4 by 4 or 5 by 5, it's called a square matrix. Okay. Now what are we going to do with these things? Well, in the last section we talked about solving systems of equations by performing row operations and certain tasks and achieving a certain kind of form. And we talked about the row echelon form. Well, we're going to do exactly the same thing here. You see, all of the things that we did in the last section did not involve the x's and y's and z's that were involved in the problem. Those were only there for position purposes. And the equal signs also were not necessary. So we could have performed all of the same exact tasks and not really had equations involved in the problems. So if we look at this from a matrix standpoint and think about rows instead of equations, you see then exactly the same kind of idea prevails. And if we're taking our augmented matrix and trying to put it into a fashion where we can read answers or where we can back substitute, then the row echelon form would look like this. You see, we can manipulate this rascal into a form like this and understand that this means 1x minus 2y plus 2z is equal to 9. And this means, well, you see, all of these say something about an equation, or they're related to an equation. So this equation would be no x, no y, 1z equals 3. Oh, z equals 3. You see, we could go back into the equation format and back substitute in order to solve the matrix. Solve the system of equations. So that's what we're going to do. Now, let's understand, let's remember that in the last section we talked about 3 things that we could do with our equations, our system of equations. We could take one equation and replace it with another. We could just swap 2 equations. Well, here in talking about matrices, we're talking about rows of numbers. So we can just swap rows. Okay, we're going to do that. We can also multiply through an equation from the last section. Well, here we can multiply through a row by a certain number. We can add one row to another, just like we added a couple of equations in the last segment. So the similarities are very direct here with what we've already done. Let's go through the process. Here's the augmented matrix corresponding with the system of equations that we started with. Now we want to achieve this row echelon form. And that row echelon form means to create a 1, to have a 1 in the upper left-hand corner, and then zeros below that 1, and then a 1 along this diagonal, and then a 0 below that 1, and then a 1 along this main diagonal. And we want to perform those tasks in the order in which I just described them. So the first task is to cause a 1 to occur in the upper left-hand corner. That job is done. The next task is to cause these two entries to be zeros. And to do that, we'll bring down the first row and think about what operations need to be performed to achieve that goal. So the first row is 1, -2, 2, 9. All right, now think about what needs to happen in order for these two entries to be 0. All we're going to do is play these two off of one another in order to make the 0 occur here. So we're just going to need to add these two because 1 with -1 is 0. So we're just taking row 1 and adding row 2. And adding these two rows, we get 0 here as expected. Adding these two rows, -2 with 3, that's 1. Adding these two rows, we get 2. Adding these two, we get 5. Now we're thinking about what needs to happen, playing these two off of one another for this entry to be a 0. Well, we need to multiply up here by -2 and then add row 3. So it'll be -2 times row 1 plus row 3. So -2 times 1 is -2 plus 2, 0 as expected. -2 times -2 is 4. 4 minus 5 is -1. -2 times 2 is -4 plus 1 is -3. -2 times 9 is -18 plus 10 is -8. All right, now we look at what we have. We've achieved a 1 up here, zeros below. Then we look to cause this entry along the diagonal to be a 1. That's already occurred. It kind of occurred naturally here in this problem. Our next task would be to cause this entry to become a 0. All right, with that in mind then, we'll first bring down our first two rows because they're in exactly the condition we would like for them to be in. Now, in order to achieve a 0 here, we're working with the second two rows, row 2 and row 3. And all we need to do is add those two rows and put the results here in row 3 in order to accomplish this 0 in this position. So adding the two rows, well, let's see, we're just taking row 2 and adding row 3. Now, it's a trivial operation here. 0 and 0 is just 0. Adding these two, we get 0 as expected. Adding these two, 2 with -3 is -1. And then 5 with -8 is -3. Okay, we have a 1 here, 0's below. A 1 here, a 0 below. Next item of business would be to have a 1 in this position. We have -1, so we need to go through and multiply here by -1 or divide by -1. So what we can do then is come up here, write down the first two rows because they're in good shape, and our instruction now is to take the negative of row 3. So we would have 0, 0, 1, 3. Now at this point we're in row echelon form, and we could write the equations corresponding with these rows and then go through the back substitution process that we used in the last section. Another way to proceed, though, and one that's rather clever, is to stay with this matrix format and actually go to a form that looks like this. It is one where, now these are the important things that we were trying to achieve. Now, I don't care what's over here. Those are some kinds of numbers. All right, but what we can do from here is to go through a few more steps and achieve zeros above this 1 and then a 0 above this 1, and then look at what we have. We have, in the equation format, we have 1x, no y's, no z's, equals a number. So x equals that. y equals this, z equals this. So by staying with this matrix format and going through a couple of additional very simple steps, we're going to make the matrix tell us the complete solution, the complete ordered triplet for solving this system of equations. Here's how it goes. Now I say these are simple steps because most of what we do arithmetically is trivial. Let me show you what I mean. Now our thinking in continuing with the matrix format is from the bottom of the matrix to the top. When we first started the process, we started with the top row and we caused this entry to become a 1. And then we kind of work below, work below, work below. And now our thinking changes because we're going to consider our last row to be in great shape, and we're going to consider that we're working above. So we want to cause these two entries to become zeros. Now, to cause this entry to be a 0 right here, we're going to work with these two. You see, we're going to operate here and add to that. So it's going to be negative 2 times row 3 and add row 2. So it's negative 2 times row 3 and add row 2. Now, I said this is relatively trivial. Look at what happens right here. Negative 2 times 0 is 0, plus 0 is 0. Nothing to do. Negative 2 times 0 is 0, plus 1 is 1. Really nothing to do. Negative 2 times 1 is negative 2, plus 2 is 0. And we set it up to be that way. So all of these operations were trivial, and all the action is over here with our constants. All right, so let's see. Negative 2 times row 3, that's negative 2 times 3 is negative 6. Negative 6 plus 5 is negative 1. All right, now, same idea, working our way all the way to the top. We're going to work these two off of one another, you see, and we want this entry to be a 0. So it's negative 2 times row 3 plus row 1. So negative 2 times row 3 plus row 1. And once again, it's trivial until we get to the constants, because think about it. It's negative 2 times 0 plus 1. Negative 2 times 0 plus negative 2. Negative 2 times 1 plus plus 2. That's 0, as we expected. We set it up for that to happen. So here's where our action occurs. Negative 2 times row 3, that's negative 6, plus row 1. So negative 6 plus 9 is 3. All right, we're almost there. One more step and we're done. Now, our last row is in great shape, and our second row is in great shape. So we have 0, 0, 1, 3 for row 3, and then 0, 1, 0, negative 1 for row 2. Now we'd like to cause this entry to become a 0, and we're working with these two rows. So it's 2 times the 1, you see, and then plus the negative 2. So it's 2 times row 2 plus row 1. 2 times row 2 plus row 1. And once again, all the action is over at the constants, because 2 times 0 is 0 plus 1 is 1. 2 times 1 is 2 minus 2 is 0, as expected. We set it up to be that way. 2 times 0 is 0 plus 0 is 0. You see, so here's where the action is. 2 times row 2, that's 2 times negative 1 is negative 2. Negative 2 plus 3 is 1. Now look at what this says. If we go to the equation format, we have 1x plus no y's plus no z's equals 1. That just says x equals 1. And this says no x's plus 1y plus no z's equals negative 1. Y then equals negative 1. No x's and no y's and 1 z equals 3. Z equals 3. So our ordered triplet is 1, negative 1, 3 for the answer into our system of equations. This form, by the way, is called reduced echelon form. We talked about row echelon form earlier. This is called reduced echelon form, continuing to where we have a pattern of 1s along a diagonal here, and then 0s below those 1s and 0s above those 1s, and our constants over here. Okay, and notice that the constants represent our ordered triplet, 1, negative 1, 3. Okay, let's go through the process again on this system of equations. Now, the first thing to do when we see the system of equations is to make sure that a pattern is established here. We want the x terms written first, and then the y terms, and then the z terms, an equal sign, and then some constants. All right, that's the pattern that we had earlier, and that's been accomplished here. Now we simply write the augmented matrix associated with the system of equations, and we can write that rather easily. Let's see, we have 1, -2, -1, and then 6. Now notice the space that I'm putting between these numbers. I tried to do that in the previous one, but I want to emphasize it here. Organization is very important in achieving a good result with these kinds of problems. So try to be rather precise in the positioning of your numbers and all of that kind of thing, and the instructions that you write to the left as well in just a little bit. Okay, we have no x here, 1 y, so that's 0, and then 1, and then 4 for z, and 5 for the constant. And then along the next row, we have 4, 2, 3, 8. Okay, and away we go. We're thinking, well, we need a 1 in the upper left-hand corner, job done. All right, that's done, so we'll bring down that first row. All right, now we'd like to cause zeros to occur below. Oh, it's already occurred here in row number 2, so we'll just bring those rascals down. Now, in order for us to achieve a 0 here, we play these two off of one another. So it's going to be -4 times 1 plus 4. So it's -4 times row 1 plus row 3. So -4 times 1 is -4 plus 4, 0 as expected. -4 times -2, that's 8, plus 2 is 10. -4 times -1 is 4 plus 3, 7. -4 times 6, -24. -24 plus 8 is -16. Numbers are getting a little big. Are we afraid? No. All right, here we go. Now, these two rows are in good shape. Now, notice the 1 here along the diagonal. Our next job is to cause this entry to be a 0. So, how do we do that? Well, we're going to need to multiply in row 2 by -10 and then add row 3. All right, let's put that instruction up here. So we have 1, -2, -1, 6, and then 0, 1, 4, 5. All right, I'm just verifying. Now, we're going to need to perform this operation. It's going to be -10 times row 2 plus row 3. All right, and we'll get a 0 in this position. Now, these two are pretty hefty numbers. Come back down here and take a look. I'm going to perform the operations here, but it's -10. I'm reading from up there. -10 times row 2 plus row 3. So -10 times 4 is -40. -40 plus 7, -40 plus 7, you see, is going to be -33. So -33 is going to go in this position right up there. I'll bring it up in just a minute. But let's make sure about this one as well. -10 times 5 is -50. And then plus -16. And that's -66. Okay, and that's going to go in that last entry. All right, let's put those in. -33 and -66 right up here. All right, next order of business is to cause this entry to be a 1. All right, let's not get ahead of ourselves. We want to bring down, whoops. I need to take my own advice and not get ahead of myself. Let's see, we need to rewrite this, the 1, -2, -1, 6, and then 0, 1, 4, 5. All right, here we go. Now we'd like to cause this entry to be a 1, so we'll divide through by -33. That is, we're taking row 3 and we're dividing by -33. Divide this by -33, divide that by -33, trivial, trivial. Divide this by -33, 1. Divide this by -33, we get 2. Let's continue to the reduced echelon form. We're working from the bottom of the matrix to the top, so we bring down this bottom row. We bring down row 3. Now we're looking above this 1 to cause these entries, the entries that are in these positions here, to become zeros. And we play these two off of one another in order to cause that entry to be a 0. It's negative 4 times 1 plus 4. So it's negative 4 times row 3 plus row 2. And again, all the action is at the constant. So we can just bring this down, just bring that down, bring this down. This is going to be a 0 as expected, and now concentrate on the constants. Negative 4 times row 3, that's negative 4 times 2 is negative 8. Negative 8 plus 5 is negative 3. All right, now look at this. All we have to do is add these two rows in order to accomplish a 0 in this position. So we're taking row 3 and we're adding row 1. So add these, add those, add those, add these. One more step and we're done. Now these two rows are in great shape. They're in exactly the form that we want them, so we'll just bring them down. And then the second row as well. Now we'd like to cause this entry to become a 0. We're going to play these two off of one another. So it's 2 times row 2 plus row 1. 2 times row 2 plus row 1. So let's see. This is trivial, trivial, trivial. 2 times row 2, that's 2 times negative 3 is negative 6. Negative 6 plus 8 is 2. Now, this says x is 2, y is negative 3, z is 2. So the ordered triplet that solves the system of equations is 2, negative 3, 2. Now, as you might expect, the funny situations that we talked about in the last section, the situations where there are many solutions, an infinite number of solutions, or where there are no solutions may emerge in this format as easily as they did before. And those situations emerge in exactly the same way that they emerged before. That is, as you're manipulating, and usually it'll happen here. Let's backtrack over to this. Oh, wait, we don't have to back up. Let's stay over here. My cameraman is going nuts now. But right about in here where we're performing some kind of operation in order to get to the bottom of the matrix, something will happen and we'll get 0, 0, or we'll get 0, negative 3, or some sort of thing like that. But all of the constants go out. We're going to get a 0 here, and then fright should set in, or some kind of bell should go off and say, this doesn't look quite right. Because if we have zeros across the bottom here, it means we have no variables whatsoever. And then you look at that constant. And if that constant is a 0, then you have a true statement here. And therefore, and if you have a true statement, it means that you have an infinite number of solutions to the system. And you go through and investigate the infinitude of answers by writing these two equations and going through the same little process that we did in the previous section. Now, if this is a false statement, if you have 0 equals 5, for example, then all of the variables have disappeared from your system of equations, from your matrix here, and you have a false statement at the end. And in that circumstance, you have no solutions to the system of equations. Here's a problem that leads to a system of equations that we can solve by using a matrix. It says find the equation of the parabola y equals ax squared plus bx plus c that passes through the points 1, 7, 2, 12, and 3, 19. Now, the equation given here is the form of the equation that we're looking for. So what we're looking for in the problem is the value of a, b, and c to place within this general form of the quadratic equation. We'll begin with that equation. And you know that the ordered pairs here, the 1, 7, 2, 12, and so forth, are simply values that we can place within the equation. So if we let x be 1 and y be 7, you see we're forming an equation in terms of a, b, and c. And this becomes one of the equations in our system. It's simply 7 is equal to a plus b plus c. Now the other equations are found in a similar way. Just use that general form and replace y with 12 in this case, and then x with 2. Of course, 2 squared will be 4, and the first term will be 4a, and b times 2 will simply be 2b. But the idea is that we place the values of x and y into the general form of the equation. Here, y is replaced with 19, x is replaced with 3, and then we simply simplify on the right side of that equation. Well, at this point, we have 3 equations and 3 unknowns, and we're looking for the values of a, b, and c. We're a little more used to seeing the equations in this form. Now, let's solve the system. We're going to use a matrix, and remember, the matrix contains none of the letters that are involved here. We're going away from this equation format into the matrix format. And in that format, we want to emphasize the coefficients 1 on the letters that don't have a coefficient, because we're going to simply remove those letters. So we'll take out the letters and the equal signs, and then the matrix looks like this. We'll tighten things up a little bit and use the little brackets to show that we have a matrix. Now remember, our concept is to cause the matrix to have entries like this in these positions. And we are allowed to swap rows, we're allowed to multiply in any row and add to another row and so on. Well, our first job is to cause the entry in the upper left-hand corner to become a 1, and we can do that by simply swapping the top row with the bottom row. Now, here's what we're doing. We're just swapping these 2 rows, but the way we indicate it is like this. We set up a matrix below, and then we indicate what we're doing to the left of that matrix, and then we'll do that. All right, so we're swapping those 2 rows here. All right, the next thing we want to do is cause our 2 entries, well, these 2 entries, to become zeros. Now, we'll work on them one at a time, but the way we approach the problem is we set up a matrix below, and we bring down the first row because we're not operating on that row. And now we decide what we're going to do. Now, here are the operations that we're going to perform. It's -4 times row 1 plus row 2. The concept is that we're performing an operation on a previous row or another row, and then we're adding the row that we're in. And that's kind of an important idea to keep in mind when we're deciding what we have to do. So remember now, it's -4 times the entry in row 1 plus the entry in row 2. All right, and this is what it's all about. Now, performing these operations, we get 0 as expected. Now, since we're doing that to accomplish the 0 in this position, we have to do this same kind of thing throughout the row. So it's -4 times each of the entries in row 1 plus the entries in row 2. And performing the operations, we get -2 in this position, and then -4 times 1 plus 1 gives us -3 here, and then -16 in this position. All right, for the next row, you know, what we're trying to do is accomplish a 0 in the lower left-hand corner. So it's some operation times row 1 plus the item in the row that we're in, that is, plus row 3. So we're deciding what, something times the item in row 1 plus the item in row 3 is going to give us 0. And we have to decide what that item is. What are we multiplying times 1? Well, it turns out, of course, to be -9. And as a result, we need to multiply -9 times every item in row 1 and then add the items that are in row 3. Now, as a result, the -9 times 1 plus 3 gives -6. And then -9 times 1 plus 1 gives -8. And then -9 times 7 plus 19 gives -44. Our next job, remember, is to cause the -2 to become a 1. Now, we're looking at the -2. We'd like it to become a 1. And usually we play the -2 off of the -6. That is, we play these 2 entries against one another. But notice they're both even. And therefore, multiples of these 2 will give us even amounts, and therefore the multiples cannot differ by 1. So what we're forced to do is work within row 2 alone. So what we'll do is we'll take row 2 and we'll divide row 2 by -2 to accomplish the entry that we're after. Now, performing that operation, we get these entries, and notice the fraction here. Now, as a housekeeping matter, in row 3, we might notice that all 3 of the entries are even, and therefore we could reduce our work just a little bit by dividing through by 2. Now, we don't have to do this, but it's an option for us, and we'll go ahead and take advantage of that in this case. All right, what do we have to do next? Well, we need to cause the -3 in row 3 to become a 0. And in order to do that, we're deciding on an operation, you see, that involves these two rows. Well, we'll decide then to multiply in row 2 by 3, you see, and then add row 3. So it's 3 in row 2 plus row 3. And of course we get zeros as these entries, and the operations are rather simple. But look at the next operation. It's involving these two entries, and so it'll be 3 times 3 over 2. You see, that'll be 9 over 2, or 4.5, and then plus -4. So 4.5 minus 4, you see, would give us the 1/2. And now for the last entry, it'll turn out to be 3 times 8, you see, then plus -22, or simply 2. Well, our next job now is to cause the 1/2, which is in the third row, to become a 1, and we're working only in row 3. So we'll set up our matrix and bring down the first two rows, and we'll indicate what we're going to do. We're simply going to multiply in row 3 by 2. So it's 2 times row 3. And multiplying through by 2, of course, we get these entries. Now, we've accomplished the pattern that we're looking for, that is the diagonal 1s with the zeros below. Now, this is called echelon form. At this point in our problem, we could take our matrix and change into a system of equations, and through a process of back substitution, find the values of A, B, and C. But why don't we continue within the matrix format and cause these entries to become zeros? Well, in order to accomplish that, we'll begin in row 3. That is, row 3 is in the condition that we're after. And we're really looking to work in the rows above. That is, we're operating on the above rows pretty much, and we're playing them against row 3. Here, for example, to cause the 3 over 2 to become a 0, we're playing these two entries against one another. And we're deciding what operation times row 3, what operation in row 3 plus row 2 will give a 0 in that particular position. And of course it is -3 over 2 times row 3 plus row 2. Now the operations for the first three entries are fairly trivial. All of the action is at the sort of the end or the right side of our matrix. -3 over 2 times row 3, that is -3 over 2 times 4, would give -12 over 2, or -6. Plus row 2 means plus 8. So -6 plus 8 will give 2 in this position. Now what we want to do is play the ones against one another. That is, we're looking at these two entries, and we're deciding what operation on the row 3 entry plus row 1 will cause a 0 to occur. And of course it's the negative of, or -1 times row 3 plus row 1. Now these entries are relatively trivial. But so it's the negative of the entry in row 3, which is the negative of 4 plus 7, will give 3 in the upper right-hand position. Well, we have almost accomplished what we're after. That is, we have almost gotten ourselves to the reduced echelon form with those little zeros above the 1s. Let's bring down the last two rows, and we're only operating in row 1. Now we're looking above, and we're trying to make this entry become a 0. And to do that, we're playing these two entries against one another, and we're simply deciding what operation in row 2 plus row 1 will accomplish a 0 in row 1. And it turns out to be simply the negative of the items in row 2 plus the items in row 1. So the first three items are trivial, and now we're thinking, well, let's see, the negative of the item in row 2, that's the negative of 2, plus the item in row 1, that's 3. So -2 plus 3, that gives us a 1 as the upper right-hand entry. Well, now we've accomplished the reduced echelon form, but what do we really have here? Well, we know that the matrix corresponds to a system of equations, and we simply have this system of equations. And of course, the 0 coefficients will cause all of these items to disappear, and the 1s will simply not be written. So what we have is A equals 1, B is equal to 2, C is equal to 4. And now back into the general form of the quadratic, we can replace A, B, and C with these values that we've found, and we're answering the question that was posed at the beginning of the problem. Now this kind of problem is called a curve fitting problem. Remember, we were given points that would appear on some graph, some parabolic curve, and we are simply generating the equation for